Welcome to the first video of the Physics Paper 1 USCE. This is for A level and it's meant for Senior 5 and Senior 6 students in Uganda. And we are starting with gravitation. This is video 1 of gravitation. There will still be I think something like 2 or 3 more videos, so we may have a total of 4 to 5 videos all covering this topic of gravitation. Please, I still emphasize this is for Senior 5 and Senior 6. If you are in a O level, please just browse and check other videos. This is not meant for you, it's for your elder brother or sister who is in A level. And I'm the presenter, the teacher at Taroma Christian High School. My name is Mandy Dennis, and I'm a Ugandan. That's why I decorated this, that way. Welcome aboard, my students, during this time of the coronavirus disease, COVID-19 lockdown. And I request you to go through these videos that I'll be uploading here, do the exercises therein, and submit your solutions so that we can learn together. You have no excuse for not getting an A. Assuredly speaking, we have enough A's. You can have as many as possible if you work for them. So please, let's do the needful. I want us to dive straight into the topic. Now, in this chapter of gravitation, we deal with the motion of the planets around the sun. We deal with the communication satellites placed around the Earth and even the moon satellites. So it's a very interesting section of Physics Paper 1, actually. So interesting. We learn a lot about the cosmos, about the space, and therefore be ready to learn. Where you find questions, feel free to research more on YouTube, Google. You can even ask me and you'll find the solutions to your questions. And just like electric fields and magnetic fields around the charges and magnets respectively, masses have gravitational fields around them. Now I want you just to think about this. We know that if you have if you have a charge, if you find a charge, let me try to make some drawing. If we have a charged body, for example, if this is a positive charge, there is going to be an electric field around it. Yes, you draw. There is an electric field. You indicate you've done this in paper 2. Yes. Now, even if you have a magnet, still if you have a magnet and this is the north and this is the south, there will be a magnetic field around. There will be a magnetic field around it. And the magnetic field lines run from north to south. You remember that? Okay. So we are saying even masses have gravitational fields around them. So around any mass, there is that force that attracts it to other masses, and that's what we call the gravitational force. Now, there is a gravitational field around any mass. Like any charge will have an electric field, and any magnet will have a magnetic field. Every mass or any mass will have a gravitational field around it. Don't call it, because the other one was electric, so we had an electric field and a magnetic field. Don't call it a massive field. It's called a gravitational field. Now we want to look at Newton's law of gravitation. Newton did a lot of research in many branches of physics. He never left out this area of gravitation, and he stated what we call the universal law of gravitation, stated by Newton, Sir Isaac Newton. It's a very interesting law. It states that every particle in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of their distance apart. Now, if you remember, in electrostatics, you talked about that force of attraction between charges. it's just similar to this, just because here we are dealing with the masses. So we are saying that Newton's law of gravitation states that every particle in the universe, every particle, even you there, you as a person, as a student, you are a particle in the universe. Every particle in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of their distance apart. So what we mean by this is that if you have two particles, if you have two bodies, for example, in the universe, you have a body of mass m1 and you have another body of mass m2. If these are two particles in the universe, so there will be a force of attraction between these two, and if the distance between their centers, between them, let me say the distance between them is r, so we are saying that that force which exists between these two masses is going to be directly proportional to the product of the masses and inversely proportional to the square of their distance apart. So let's state it again. Newton's law of gravitation states that every particle in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of their distance apart. You know, you can go further and simplify this. You can simplify this, and where there is a disproportionality sign, you write and put an equal sign and a constant. So we can write it like this. Yeah, F is equal to K m1 m2 over r squared. Later we shall learn that this K has a special name. Yeah. Okay. And this is exactly what I've just done using the hand. That F, the force of attraction between those two masses, is going to be directly proportional to the product of the masses, the product m1 m times m2, and inversely proportional to the square of their separation or their distance apart. Where m1 and m2 are the masses and r is the distance between them. Now, if you simplify here, last time I told you that we can write this where there is an equal sign, we put, where there is a proportionality sign, we put an equal sign and a constant of proportionality. But it has a special name, so we use a capital G. G. I don't know how you pronounce it best, but use a capital G, a letter G. So we are writing F is equal to G m1 m2 over r squared. That capital G is called the universal gravitational constant, and it has a value that is 6.66, actually 6.67 exponent negative 11 Newton meters squared per kilogram squared. We shall learn how we get those units later. I just want you to pay close attention to this equation. We shall use it in the whole of this topic. We shall need it. It's the most important, the very most important equation. That is F is equal to G m1 m2 over r squared. The value of G is always given. This capital G is given on the first page of your examination paper, P510/1, that's first page. Okay, now, how do we get the dimensions of capital G? How do we get the dimensions of capital G? How do we get the dimensions? Now, remember, from F is equal to G m1 m2 over r squared, I told you never to forget this. We can make G the subject. If you make G the subject, mathematically, anyone can rearrange this way. So we have that F r squared divided by m1 m2 will give us the G. So implying that now the dimensions of G, so we shall take the dimensions of F, dimensions of r squared, divided by the dimensions of m1 and m2 multiplied. The dimensions of force, remember this is mass times acceleration, so we shall have capital M, LT power negative 2. M, LT power negative 2, that's for the force. And the radius, or the distance, r squared, distance between them is a length, so you say capital L squared. And then for the masses, mass 1 and mass 2, that's just m. Now when you deal with some little indices here, which you did in S2, you realize that you're going to end up with L times L squared, you get L power 3, T power negative 2, and M power negative 1. This will cancel with that, you'll have M power negative 1. L power negative 3, that's meter. Actually, if you can even use this to get the units very easily. L power 3, these are the dimensions of the universal gravitational constant. So we have L power 3, T power negative 2, and M power negative 1. So therefore the units of G can also be M power 3, that's for the length. Then this is per kilogram and per second squared. This is also similar to what we wrote previously. We said N, you can have the newtons. You can actually just pick it direct from here. Look at this. You can pick it straight from here, that you have the force. This is newtons, meter squared, and then per kilogram squared as the units. Yeah, I hope you understood that. Let me express it with a pen here. We are saying that the units of capital G, you can write newtons. I've obtained that from here, and then from here we have meter squared, and then here we have kilogram. But remember, it's in the denominator, kilogram squared, so we put like that. So these are the units of G, or these ones. They all work. They are all correct. Okay. Now, the laboratory determination of the gravitational constant G by Boy's method. Boy has the best method. There is also one by Cavendish, but we are using here in this lesson, I'm talking about Boy's method of determination of the gravitational constant. And this is a setup, a very simple setup. Please master this setup. It's a very simple one. We are going to have a polished bar. Actually, it's this one here. A polished bar. This is a polished bar. So, if you are drawing this, you start with a polished bar. We have just a bar like this. A bar. And you connect a torsion wire or a quartz wire. Then, you put two gold spheres. They should be identical. One should be shorter and one longer, like I've indicated here. This is the polished bar, and then we have the torsion wire here, that holds it. So it's suspended on a torsion wire or quartz wire. Then we have here two gold. We have here here we have gold spheres, and they're identical, A and B. Now, next to these, we will have lead spheres, bigger ones, and they should also be of identical masses. And this setup should be shielded from wind currents, because remember, you're going to measure a very small angle. So from the aerial view of that setup, this is what you will have. You will have the lead spheres here, A and B, and the gold spheres A and B. These are, for the gold spheres, we are using small letters. Okay. Look at this diagram and please study it properly. We are going to look at the procedures, but you still keep referring back. So we are saying two identical gold spheres A and B, each of mass m, are suspended as shown above from the ends of a highly polished bar CD of length L. So we have the polished bar of length L, and it's highly polished. The polished bar is suspended by a short fine quartz wire. Two large lead spheres A and B, each of mass m, so they should be identical, are brought in position near A and B respectively. the distance d between A and B, or between between small a and capital A, or between small b and capital B is measured and recorded. You measure that small distance. Let me first go back. You see, that distance d. So you have to measure a very small distance. The distance between this and that distance there, we are calling it d. Even here, the distance between these two, that distance d, is measured. Between the centers, is measured and recorded. Now, the deflection theta of the bar CD is measured by the lamp and scale method, and it's recorded. I'll go back still to the diagram. Look at this. Because capital A attracted small a, this is a lead sphere attracting a gold sphere. They attracted each other. They came closer. You see, initially, this polished bar was in this position. It was horizontal. Not really horizontal, because this is the aerial view. You are seeing from above. You are seeing from up this way. You're putting your eye this way. So this is what you see. Now, this A was initially here, so it has been pulled this side, and even B was initially here, it has been pulled here. You measure the distance between them, which is D. Distance between them, and we are talking about this theta here, that angle of twist, which we are calling the deflection. Which we are calling the deflection. So the deflection theta of the bar CD is measured by the lamp and scale method, and it's recorded. Now, we don't need to go into the details of the lamp and scale method of measuring those small angles. So all you have to know is that we are having and by the way, we have the lamp and scale method, and it's the reason why this bar has to be highly polished. Please take the trouble to research more about this if you want to know the lamp and scale method and why the bar is polished. Now, you realize that because on that polished bar, there are two forces acting in opposite directions, so they constitute a couple. So the torque of the couple on CD will equate to the torque on the so this is the force from Newton's law. You remember that G, the force is equal to the product of the masses over the square of the distance between the masses, but we multiply by the gravitational constant. So this is the force, and to get the torque of a couple, you get that force times the distance between the two forces. I'll take you back a little. We want there is a force here. There is a force here. Let me say there is a force here, which we can call F. Come on, F. Even this side there is a force F, and they're acting in opposite directions. You can say here, and then this one is acting in that way. So they constitute a couple. And how do you get, if the distance from here up to here, from A up to B is L. In simple terms, the length of CD is L. So to get the torque of that couple, you just get F times L. You remember that from O level. So we are going to say torque of the couple on CD is equal to capital G mm over d squared. This is the mass of the gold sphere times the mass of the lead sphere over d squared times L. And it implies that now we are going to have that this torque here, torque of that couple on CD, is equal to C theta. Now what is C? C has a special name. C is what we call the torsion of the wire, that quasi wire, per radian of twist. This one here, it's a constant, then times the theta. Now this value here, C theta, is equates, actually this is also the torque, the twist, the restoring torque as you twist that quasi wire. When it twists, that's the restoring torque, which is c theta. So it should be equal to the torque on the CD at equilibrium. So once you have this, where C is the torsion of wire per radian of twist, thus G can be calculated. Just make G the subject here. We know the mass M, we know the mass of the gold, the mass of the gold sphere, the mass of the lead sphere. We know D, and we know L, and this is also known. So we have measured this, so you can easily get the value of the gravitation constant. Remember, we said it's equal to 6.67 exponent negative 11 Newton meters squared per kilogram squared. Okay, I will dive into something very interesting. Kepler, you really did something so wonderful in physics. Kepler's laws of planetary motion. I will show you a short video just to demonstrate, but it's going to be separate from this one. Just to demonstrate Kepler's laws of planetary motion. The first one states that the planets describe ellipses about the sun as one focus. The planets describe ellipses about the sun as one focus. The second law, the imaginary line joining the sun to any planet sweeps out equal areas in equal time intervals. And the third law states that the square of the period of revolution of a planet is proportional to the cube of the mean distance from the sun to that planet, i.e. t squared is directly proportional to r power 3.